Okay, so is Professor Ananda Dasgupta here? Could you please start sharing your screen?
Am I audible?
Yes, you're audible.
Okay, I have given you the co-host permission, sir, Anand sir.
So I think Dr. Ananda Dasgupta has joined.
Hello.
Hello?
Can you hear me? That
Yes,
was my
sir.
Yes,
question.
yes, sir, we can hear you.
Okay.
Right now your video is not on.
Okay, I'm switching on my video now. Yeah.
Yes. Good morning,
It's a
sir.
bit dark, so I'm not sure whether you can see me, but still,
Yes,
a lot of
yeah,
lights on the back.
Okay, okay.
Good to see you.
Fine. Yes, good to see you, sir. So,
Okay, so I need to start sharing my screen. Let's just check
yes,
whether
yes.
that's working.
So we start sharing this.
Okay. It seems to be working. Can you all see this?
Yes, yes, sir. Just make it full screen.
Yeah, I will make it full screen. Yeah. Now it's full screen, I hope.
Yes, sir.
Okay.
Okay, so Anjay sir has already joined. He is the session chair of your session, sir.
Yeah, sorry. Somehow my Word file containing his introduction is not working. So I just very briefly introduce that Professor Ananda Dasgupta is from IISER, Kolkata. He's a professor of associate professor of physics. He did his PhD from Jadavpur University, and following that, he has been to various places before joining to IISER, Kolkata. And his research interest lies in various aspects of Lie algebra and all this. And today he is going to talk about a very interesting topic: Sherlock Holmes meets Schrodinger cat, or how the quantum can keep our secrets. Over to you, Professor Dasgupta.
Thank you for the kind introduction. And I must thank IEM for giving me the opportunity to speak here. I'm just hoping my network holds up. So maybe I will just switch off my video for the time being because, or does it be? Let's see. So it's always a very tough act to follow up on Krishnendu's talk. And Krishnendu, of course, gave a very advanced talk. And my talk will be very tame in comparison, but it was meant to be that. This is basically a popular level talk. Let's just put it that way. And in that vein, I will start with Sherlock Holmes. And I'm pretty sure all of you, at least most of you, must have read this particular story. And for those of you who haven't read this particular story, The Adventure of the Dancing Men, I definitely recommend that you read it. And therefore, I will not really give you any spoilers for the story. But our interest in this particular story at this point is this, that the story starts basically with a weird kind of message, which a particular person finds and brings to Holmes to sort of understand what it's all about. I'm not going to talk of the whole story. I'm just going to point out that Holmes actually says in between, I am fairly familiar with all forms of secret writings, and I'm myself the author of a trifling monograph on the subject in which I analyze 160 separate ciphers, but I confess that this is entirely new to me. But what is important is at the end of the story, Holmes actually can crack the cipher and communicates with the person sending the cipher, the semi-villain of the story, via this cipher. And the important point here is what one man can invent, another can discover. That's what Holmes said at the end. In other words, the idea was codes, no matter how complicated they are, can be broken. Now, this is in itself a fascinating story, and I can keep on talking about this for hours, the theory of how codes can be written and broken and so on. But frankly, for the want of time, I will want to move on quickly to my actual topic today. So, but what I can really talk about here is this. Okay, this is again not really my main topic, but just as an introduction. The machine that you can see on your screen right now is a very famous machine. It's called the Enigma. This was used by the German forces for communicating in secret during the Second World War. And the story of how the Allies actually broke the Enigma code and really managed to intercept a lot of these coded messages is very fascinating, and it would make a wonderful film. In fact, it has been made into films, in fact, 2 actually. And this particular person whose picture you see on the screen right now is a very famous spy, Vera Atkins. And one of her major achievements was that she managed to smuggle out a copy of the Enigma machine from Poland when it had just fallen to German occupation. Vera Atkins actually has led a very fascinating life. And for those of you who are film buffs, a recent film, A Call to Spy, in which actually talks about Noor Inayat Khan and other very important people in the struggle against the Axis at that time, Vera Atkins plays a central role in that. But the person who really played a major role in cracking the Enigma code is this person, Alan Turing, who is, of course, well known as the father of modern computing science in a way. And one of his major achievements during the war was being able to crack the Enigma code so that the Allies could intercept and understand what the Axis powers were talking about. Once again, the theme being codes once written can be broken. But nowadays, especially during our commercial transactions and all, we do need coding which can't be cracked. And most of modern coding, not all of it, but most of modern cryptography is basically based on what is called the public key system or asymmetric key system. And one of the most common and well-known versions of that is the so-called RSA. This is named after the originators, Ron Rivest, Adi Shabir, and Len Adelman, the 3 people. In fact, frankly, RSA was actually invented way before these 3, but it was invented in the British GCHQ, the division which actually works in code making and code breaking in the British Secret Service. And because it was classified at that time, the original discoverer of this could not publish way off until a long time after RSA had actually published their results openly. So we still call this the RSA code. And the British gentleman who actually discovered this originally is somebody whose name is not really very well known. Now, I want to just give you a very brief overview about how RSA is actually used. Okay, I hope I am audible because I'm not getting any feedback right now.
Yes, you are audible.
Okay.
Sure, please go ahead.
Okay. Now, I will give you a very brief introduction to what RSA is, or at least how it works. I'm not going to go into the mathematical theory of it simply because it will take a long time to talk about it. And also because it's really not our major concern here. So the idea behind the RSA protocol is the following. We have 2 people who want to communicate, and in cryptography, it's almost universally true that the 2 people are A and B but we don't call them A and B, we call them Alice and Bob. So suppose Alice wants to send a message to Bob. Now the message can be anything, but as you all know, any communication can ultimately be converted to a number. So let's just assume that Alice wants to send a number. Let's say this number is A. Now, Bob has to do some preparation before Alice can send him the message. And the preparation that Bob has to do is the following. Bob has to choose two very large prime numbers, P and Q, maybe 200 digits each, so that the product is a number which has roughly 400 digits. So it's a huge, huge number. Now, I'm going to illustrate this process, but of course, I cannot really illustrate this using 400-digit numbers that would fill up my screen. So I'm going to use two very small numbers so that the calculation should be easy to understand. So the numbers, for example, that Bob could choose, let's just pretend that they are 200 digits long, but they're really just 3 and 5, two prime numbers. Now, what Bob has to do with these numbers is, first of all, he has to calculate P minus 1 into Q minus 1, which in this case is, of course, 2 into 4, that's 8. And he has to choose a large number C co-prime. That is a number which doesn't have any common factors with this P minus 1, Q minus 1. So in our example, P minus 1 times Q minus 1 is 8. So Bob has to choose a number, another integer, which is co-prime to 8. Something between 1 to 8, which is not prime, doesn't share any common factor with it. So let's say Bob chooses 3. 3 is, of course, co-prime to 8. It happens to be a prime, but you don't need it to be a prime. All you need is that it doesn't share a common factor with P minus 1 into Q minus 1. The next step that Bob takes is calculates the multiplicative inverse of 3 modulo 8. That is, he finds out the multiplicative inverse D of this number C, but it does that modulo P minus 1 Q times Q minus 1. So he has to find out a number which, when multiplied by C, in this case 3, gives you 1. It's an integer, but of course, remember, we are doing modulo 8 arithmetic. So here D is actually 3, because as you can easily check, 3 times 3 is 9, and 9 is the same as 1 modulo 8. In case anybody is here who does not know what modulo 8 arithmetic means, is simply remainders after you divide by 8. So D is the multiplicative inverse for the multiplication modulo 8 operation of C. So now he has these numbers. He started with two prime numbers, P and Q. He has multiplied P minus 1 and Q minus 1 and has got 8. He has this number C, which is co-prime to it. And he also has another number, which in this case happens to be the same number, but that's just a coincidence. Because we have taken a very small number, you don't have very many choices anyway. But this multiplicative inverse is unique. And so what he will do next is this. He will announce P times Q, the product, in this case 15, and C, the number he has chosen, that is 3, for all the world to know. So this is going to be public, PQ and C. So this pair is Bob's public key. And what he does is does not disclose the multiplicative inverse of C modulo P minus 1 times Q minus 1. This number 3 that he has found out in this particular example, he keeps to himself. You must realize that D in general will be very different from C and could be a vastly larger number typically. Now, here is what Alice will have to do if she wants to send a message A to Bob. The calculation that she has to do is the following. Let's say she wants to send a message, which is the number 7. So what she does is looks up Bob's public key that's usually available in a computer system. Of course, when I say Alice looks up Bob's key, it's really not Alice who will actually look up the key. It's Alice's computer that will actually look up the key. But anyway, now that she knows N and C, what Alice will do is Alice is going to calculate the result of a to raise to the power c. So this number 7, she will raise to the power 3, but she will do it modulo 15. So 7 cube, as you all know, is 343. And 330, of course, is divisible by 15. So the rest, 13, is the modulus. So Alice at the end gets the number 13, which she sends to Bob. That's the cipher text. So she wanted to send 7, but she is sending 13. 13 is the coded version of so-called cipher text. Now, once Bob gets it, how does Bob get to know what Alice wanted to send him? What he will have to do is the following. He knows D. Remember, Alice does not know the number D. She only knows a public key, N and C. And in fact, not only Alice, the world knows that. But D is something which Bob and Bob alone knows. So Bob must calculate B raised to the power D. The number that Alice has sent him, that is 13, he has to raise it to the power D, which is his secret private key. And that, in this case, is 3. And so what she has to do is calculate 13 to the power 3 modulo n. And that is going to be the original message A. 13 to the 3, straightforward calculation is 2197. But you have to do it modulo 15, and that's 7, as you can easily check. Now, the reason why all of this works is basically there's some nifty number theory behind this, Fermat's little theorem and so on. I'm not going to go into the mathematical details of this. It's very easy to find the details on the web. So if you're interested, you can just look it up. But the process is basically this. Now, the whole point as to why this works is the following. This RSA system is asymmetric. Asymmetric in the sense the encoding is done via Bob's public key, N and C, which is available to everybody. So anyone who knows your public key, which in today's world could be anybody who can have access to the internet, can send you a message. Decoding the message, on the other hand, is done via a private key, which Bob and Bob alone has. Or strictly speaking, it's Bob's computer which has that. So only the person who created that key pair and who has kept the private key to himself can read the message, nobody else. Even the person who sent the message, once she has coded it, she has no way of recovering the original message. Of course, she would have the original message with her anyway, but if she somehow lost the original message, then it would be impossible for her to recreate the message from the coded version, because the recreation can only be done via the private key. Now, one thing you might ask is, why is this really a big deal? After all the world knows N, which is P times Q, and C. So can't they just calculate D? D is simply P, the multiplicative inverse of C from the modulo P minus 1 times Q minus 1. And okay, I would like to stress at this point that all of these steps that I have stated right now, until now, can actually be done very efficiently on a computer. Once again, I'm not going to go into the details of complexity theory, which tells you exactly how complex these calculations are, but there are algorithms which allow us to calculate these results very, very fast. So the question is, why can't simply somebody just use the value of N and C and use that to recreate the value of D? And then if that person has the value of D, he can definitely recover the original message. But we could do this, but only if we had the means to do something which we have known from childhood is a rather difficult problem, or we have been told is a rather trivial problem. The problem of factorizing N to find out the two primes P and Q which make it up. Now, from childhood, we had learned about factorization as a problem, and we have learned to do it. And when as kids we found it difficult to do, our teachers called us dummies and forced us to work at it over and over again. But frankly, maybe the reason why we found factorization of a large number difficult is that because it is difficult. This is one of the hardest problems, simple to state, but hardest to do problems that we have. In fact, the current record that we have is the so-called RSA 250. It's a 250-digit semi-prime. Semi-prime means it's a product of two prime numbers. And this was factorized in February 2020 by a team of a large number of people: Paul Zimmerman, Emmanuel Thome, Nadia Henninger, and also other people. Let's not name all of them. And basically, the previous number, in fact, RSA 240, this was a 240-digit semi-prime. It was actually factorized by a huge bank of computers, not a single computer. But if you could try to do it on a single computer, which was the gold standard at that time, the 2.1 gigahertz processor speed Intel Xeon Gold 6130, it would have taken 900 years to do it. Of course, it didn't take them 900 years to actually factorize it because they were using thousands of computers running in parallel. Now, the reason why this is so hard is that, at least as so far as we know, the best algorithm we have today for factorizing large numbers is called the general number field sieve. Frankly, I don't really understand this algorithm that well, but I can see, at least Wikipedia tells me that it's roughly the complexity is n to the 1/3. Then it takes roughly n to the 1/3 steps to factorize n. N being this actual number. Okay, those of you who are well versed in computer algorithms might find n to the 1/3 to be rather slow. I think that it to be rather slow because usually we code these numbers in terms of the number of bits. Here, remember, n is the actual number, so that's exponentially large compared to the number of bits involved. Just to give an illustration, suppose with today's technology, it takes a day to factorize a 200-digit number. So n is of the order of 10 to the 200. It takes 1 day to factorize it by our modern computer. In fact, it takes a bit less nowadays, but still, it's roughly a decent estimate. So the kind of numbers which are actually used in RSA are 400-digit numbers, product of two 200-digit primes, and the number of days it will take to factorize that using the same technology is n to the 400 by 10 to the 200 to the power 1/3, n to the 1/3 basically. That's roughly 10 to the 67 days, and that in years is way more than the age of the universe. So basically, the reason why RSA is considered to be secure and why much of the world's trade and everything else is done using this is because it takes inordinately long to break even smaller RSA codes, and the actual commercial RSA codes would be impossible to break with today's conventional technology. However, conventional computer technology, of course, is not the end of the world. We all know that quantum computation has started making strides, and the person whom we can blame for this, or at least give credit for this, at least for bringing up the idea, was Richard Feynman, who first showed that if you could use computers which actually use quantum mechanics directly, many problems which cannot be solved by classical computers can be handled by them. That, of course, was a theoretical study, but as time went by, things became more and more practical. Now, the groundwork for this idea of Feynman was laid earlier by none other than Erwin Schroedinger. And again, I'm not going to spend my hour talking about the Schrodinger's cat experiment, but this particular thought experiment that is being depicted on your screens right now, the so-called Schrodinger cat experiment, which I'm pretty sure almost everybody is aware of, essentially talks about a new kind of thing which is different from a classical object, a superposition of two different states. And this linear superposition of states, which quantum mechanics allows you to have, actually produces a huge power which you can exploit using quantum mechanics when you apply it to computing. Okay, and this, it's a rather nice coincidence that only this morning I learned that Peter Shor, the person whose algorithm manages to, at least in theory, to use a quantum computer to crack factorization problems very, very rapidly, has been awarded the Millennium Prize for 2023. So he's one of the 3 co-recipients of what is the bigger Nobel Prize, at least to quote some newspapers. So that has been announced only today. And Peter Shor, okay, Shor's algorithm is a fascinating topic and something which we teach in our quantum cryptography or in our quantum computation courses. Okay, so I think there's a raised hand. So am I going to take questions now? I can take questions now if necessary.
Let's take the question at the end of the talk.
Okay.
Please go ahead.
Okay, thanks. So Shor's algorithm, again, something I'm not going to discuss today. That would take at least 2 classes of about 90 minutes each to explain properly. But basically uses something called the inverse quantum Fourier transform and does some nifty number theory and ultimately ends up with a very high probability factorizing a product of numbers. Now, in a conference in 1998, Peter Shor was introduced by Strassen Walken by quoting one of his own limericks. It was written by Jennifer, his wife, and Peter Shor himself. And you're just going to read the limerick to you. He says, if computers that you build are quantum, the spies of all factions will want them, our codes will all fail, and they will read our email till we have crypto, that's quantum, and taunt them. The important point here is our codes will all fail because most of our codes have security which is based on the fact that it is difficult to factorize the product of large numbers, at least as far as we know, using classical methods. Quantum methods, on the other hand, allows you to do the factorization in a lot smaller time. However, when Walken read out this limerick, by the way, I will actually ask you to pay attention to the last line till we have crypto, that's quantum, and tandem, because that's going to be the focus of the rest of the talk. But Strassen actually read Peter Shor's limerick and replied to it with one of his own, which went to read our email, how mean of the spies and the quantum machine, be comforted though they do not yet know how to factorize 12 or 15. That was basically because, at least at that time, Shor's algorithm was simply theoretical and people had not built quantum computers which could actually handle large numbers. Well, in this case, large numbers meaning 12 or 15. Now, this limerick was 24 years ago, to be more precise. And today's quantum computers can actually handle a lot more than the numbers that the quantum computers at 98 could do. So nowadays, 20 qubits is the sort of declared result. Nobody really knows how many bits, how many qubits, say, the armed forces quantum computers can handle, because those are secret. But in the public domain, we know of quantum computers which can handle 20 qubits or so. And so, with rapid advancement of technology, the day is not perhaps far when conventional cryptographic systems like the RSA will fail because quantum computers will become strong enough to factorize the RSA keys. Now, the important thing here is, while the quantum takes away our security, at least will take away our security, provided we wait long enough, quantum also gives you a way of producing security. And the way it does that is that it uses something which people knew long before quantum mechanics came into being, that there is one coding system which is known to be provably secure, which can never be broken. And that has nothing to do with quantum mechanics really. It's called one-time pads or Vernam ciphers. Basically, a key which 2 people share, and they use once and only once to send a message. So I'm going to simplify the process and just describe how it's done. Basically, if you have a key which I've represented by a binary number, well, after all numbers can be represented by a binary number. And let's say the message is another binary number. So Alice wants to send a message, there's 001, 011, 01, 01. to Bob, and she wants to do it securely. Bob and Alice both share the key beforehand. Somehow they have the same key. Now, the encryption is carried out by something as simple as a bitwise XOR. That is, if the two bits at the same position match, you get a 0. If they don't match, you get a 1. So in this case, 1 and 0 don't match, so you get a 1. 0 and 0 match, so you get a 0. Then you have 1, 0, and so on. So this is the cipher which is sent over to Bob. And how does Bob decipher this? The decoding actually works exactly the same way. And that is basically because XOR is self-inverse. If you do XOR twice, you get back the original result. So decoding would be, Bob has a key. Of course, he doesn't have the message, but he has a ciphertext. So Bob basically XORs bitwise the key and the cipher. So 1 and 1 gives you 0, 0 and 0 gives you 0, and so on. Then 0 and 1 gives you 1, and so on. So you can see at the end of the decoding process, the message has come back complete. That's simply because A XOR B is A. Why is this secure? Because since the key is completely random, the cipher could be consistent with any message whatsoever. The only thing you can learn from the message, even if the ciphertext is intercepted by the enemy, is that how long the message is. Nothing else can really be learned. Okay. After all, I could use an entirely random different key to get any other random combination. The reason why Alice and Bob can communicate with this is that they share the key beforehand. And this is what you call provably secure. Okay, the mathematical proof of this is a bit more complicated. It sounds a bit more complicated, but basically it's the same. It's what I said right now. This cipher, once produced, is consistent with any message of the same length. So any one of the 2 to the n messages could have given you the same cipher just by changing the key. And you don't know, at least if you are eavesdropping, you don't know what the key is. So if the one-time pads are so secure, they were called one-time pads basically because the keys were written in pads, and you were supposed, both parties were used to use the top sheet. Once you use it, clear it away and destroy it, then use the next sheet and so on. So why would anybody use anything else? Why RSA and everything else? After all, this is secure. The only problem is the 2 parties must share a common pad, and this sharing so delivering the pad from one person to the other and keeping it secure became a very major issue. In fact, extraordinary steps have been taken to ensure that the pads could be delivered and kept secure. Now, this is actually a picture from a real situation where a walnut kernel had the one-time pad rolled up inside it, and it was delivered as part of dry fruit packages. And one very important thing is, for this to be secure, the key has to be used only once. If you repeat the key, then frequency repetitions of different data combinations, etc., can be used to break the code. If you use it only once, then it's secure. In fact, it has to be known only to the legitimate parties. Nobody else should know it, and used only once. In fact, because the Soviet intelligence reused the same key several times, the American Venona project, which was managed and run primarily by women cryptographers of great skill, they managed to decrypt many of the messages. And people say that's one of the reasons why the Cold War ultimately was won, so to speak, by the Americans, simply because they could figure out many of the secret messages which the Soviets were sending. Now, so what we really need is a way to securely distribute a random key between 2 legitimate parties, the ones who are actually trying to communicate. And an eavesdropper should not be able to intercept the key, or at least if they try to intercept the key, any attempt at such intrusion should be detected. So this is what you really want. And quantum mechanics actually allows you to do this. The subject is often wrongly called quantum cryptography. It's really not quantum cryptography. We are not really coding using quantum mechanics here. We are doing what is called quantum key distribution. The key is being distributed using a quantum channel and basically using the basic ideas of quantum mechanics. Now, the basic idea behind this kind of thing came up by when Stephen Weisner first talked about things like digital currency and so on. And he came up with these ideas in the 1970s. But in the 1970s, everybody thought that the basics of quantum mechanics, the fundamentals, were really too esoteric to worry about. Practical people don't really think about those things. They only calculate eigenvalues or other experimentally observable quantities. So even though Weisner did most of his work in the 1970s, his first paper could be published only in 1983, in which he actually published quite a few very important ideas, which actually led later to things like quantum key distribution, the subject I'm talking about. Now, Charles Bennett and Giles Brassard used Weisner's idea to give the first quantum cryptography protocol. It's called BB84. BB simply because Bennett and Brassard, and 84 is the year. So not really very old. And in 89, Bennett actually teamed up with Lee Smolin and others to do a first experimental demonstration that QKD, quantum key distribution, can really be done. And Arthur Eckart, for example, in 91 came up with the E91 protocol, which uses entanglement. That's a different way of using cryptography. We are not going to talk about all of that. Now, my only original contribution to this whole talk is this. The two pictures that you see on your screen right now, I clicked them when Bennett came to Calcutta. And the right-hand panel is our colleague Prashant Panigrahi talking to Bennett in EZCC. His talk was delivered there. And there he talked about quantum key distribution. The B92, that was his algorithm, which is a simplified version of BB84. And I will take some 10 minutes to try to describe what B92 is. But before that, because I will talk about B92 and nothing else, simply because B92 is simple enough to describe quickly. So the basic idea is two friends, Alice and Bob, once again, can establish identical random keys using the B92 protocol. And if somebody else, now unfortunately this somebody else is always called Eve, so there's a sort of gender bias to this. But anyway, if Eve tries to intercept the key, she will not be able, firstly, she will not be able to recover all of it. But more importantly, the two friends who are actually communicating the key will be able to detect her intuition. That was the basic idea. In fact, that's the idea of all of these protocols. I will try to explain why this happens, why the B92 protocol does that. But before that, very quickly, just in case there's somebody here who has not gone to that level of quantum mechanics yet, let me just quickly remind you that if you have everybody knows this, right? If you have two Polaroid sheets and you rotate one with respect to the other, as you rotate the Polaroid sheet, transmitted light changes from high to low. And the way we understand this in classical theory is that after passing through the first Polaroid sheet, which is called the polarizer, light becomes polarized in a particular direction. Let's say it's horizontally polarized in the horizontal direction. But the other Polaroid sheet, which we call the analyzer, has a preferred axis, and only the component in that direction will pass through. So if you rotate the analyzer, the angle between the direction in which light is polarized after passing through the polarizer and the preferred axis, that keeps on increasing, and the component of light that goes through is simply cosine, given by cosine of theta, where theta is the angle between the two axes. And since intensity is proportional to square of the amplitude, so the intensity falls off as cos square theta. This is the very familiar law, which is called Malus law. And in particular, if you have diagonal polarization, that is, the angle is 45 degrees, then half of the intensity comes through. Half of the intensity after the first Polaroid comes from the second Polaroid. Now, understanding Malus law is easy in terms of classical wave theory of light. But how do we understand this in terms of its quantum theory? We know in quantum theory we have photons. And when you think of light as a stream of photons, when passed through this let's talk in particular about this pi by 4 or 45-degree combination. What happens is half of these photons go through. And the energy of a given photon, that's h times nu, that doesn't change. Each photon is still as energetic, only half of the photons go through. That is why the intensity falls by half. Now, that's easy enough to understand when you have a large number of photons coming in. But what if we attenuate the source so much that only a single photon arrives at the polarizer at a given time? Does it go through or does it not go through? This is what quantum mechanics tells us, that a given photon polarized horizontally initially has only a 50% probability of getting through if your analyzer is at a 45-degree angle. And the whole point is you cannot tell whether a given photon will go through or not. All you can say is there's a 50% probability of it getting through. This is an entirely random process. And the important, very important result, which is akin to the collapse of the wave packet that everybody talks about in quantum mechanics, is that the ones which do go through, their states are changed. They're no longer polarized horizontally. They're polarized along the polarized analyzer direction, that is at a 45-degree angle. Now, this is very critically important. By making an observation, you have actually changed the state of the system. Okay, so now with this background, let us talk about how Alice and Bob will generate a random key or will share a random key. First of all, what they do is sitting on their own computers, they generate two independent random strings of zeros and ones. So Alice has this string of zeros and ones, Bob has this other string. Now what Alice and Bob share is a channel through which Alice can send polarized photons to Bob. That's the so-called quantum channel. Now what Alice will do is the following. If her bit is 0, she will produce a polarized photon which is polarized in this state, that is, has a horizontal polarization, a single photon horizontally polarized. And if her bit is 1, then she will produce a single photon which is diagonally polarized. So these are the two polarizations that Alice produces depending on what bit her random string is showing at that particular stage. On the other hand, what Bob does is, if his bit is Bob actually detects the polarization state of the photon which Alice sends him. So what Bob is going to do is set his analyzer axis. So if the bit is set at 0, what Bob will do is set the pass axis diagonally. But remember, this diagonal is actually perpendicular to Alice's diagonal. And if Bob's bit is 1, he will set his polarized analyzer axis vertical. Now notice one thing. What this means is, if Alice has, say, 0 and Bob has 1 at a given position, then Alice will send a horizontally polarized photon. Bob will try to detect it in a vertical polarization state, and the probability of the photon going through in this case is exactly 0. There is no chance for the photon to get through. The same happens if Alice has a bit 1 and Bob has a bit 0, because Alice is producing light which is diagonalized like this, in this polarization state, and Bob is trying to detect it in a state which is perpendicular to that. Okay, so if Alice and Bob has different bits in their respective positions, Alice's photon will never go through Bob's polarizer. On the other hand, if Alice and Bob has the same bit, say both 0, then Alice produces a horizontal polarized photon and Bob tries to detect it at an angle of 135 degrees to the horizontal direction. Cos square 135 degrees is half, which means Bob has exactly 50% chance, or there is exactly 50% chance that the photon will go through Bob's polarizer. The same happens if they were both 1. Alice would send a diagonally polarized photon. Bob will try to detect it in a vertical direction, 45-degree angle. Cos square theta is again half. So let's just see this in action. So let's say Alice's bit was both 0 and Bob's bit was also 0. So Alice sent this photon, polarizer status was this. That was Bob's polarizer status. This is really the analyzer status. So there's a 50-50 chance of transmission. 0, 1, no chance of transmission. 1, 0, again, no chance of transmission. 1, 1, again, a 50-50 chance of transmission. So a photon will never pass if Bob and Alice have different bits. If they're the same bit, there's a 50% chance of success. Now, when the photon gets through, Alice and Bob definitely know they had the same bit. Okay. So the way in which they can share a random key is that they will start with their arbitrary keys to begin with. Whatever they had, arbitrary 0, 1, etc., whatever they had, but they will only keep. So at the end of the process, what Bob will do is pick up the telephone, or maybe take out an advertisement in next day's newspaper, telling Alice that, okay, the photon in position number 13, 17, 21, 19, 20, 24, these got through. So after that, what they will do is they will simply keep those particular bits and discard the rest. And once Bob publicly declares which photons went through, because the original strings of zeros and ones, the random ones, were known only to Alice and Bob, they were different. But now that you have chosen a subsection, these two strings will definitely match. Now you have two sets of random bits which completely are identical to each other. Now, of course, this is an idealized picture. You have to take into account the fact that there may be transmission errors and things of that kind, but I'm not going to go into those details. Of course, if you want to build a real engineering system, you will have to worry about those details. But what is important is, what if Eve tried to intercept the photons between? After all, Eve's job is to try to listen in and try to figure out what this code is, what this key is going to be. Now, once the key is known, every message which Alice sends Bob or Bob sends Alice can be cracked. Here, the problem with Eve is she will, of course, have to determine the state of the intercepted photon. Whatever photon Alice sends Bob, Eve can very well intercept it, but she will have to determine its state. Now, what she can do, one thing she can do, is try to mimic Bob. That is, put an analyzer of her own at random positions, because she doesn't, of course, know what Bob's analyzer states are, so she has to do it randomly. And the trouble is, she can only be sure of the photon state only if it passes through our analyzer. If it passes through our analyzer, she definitely knows that her state, that bit which controlled her state, is exactly the same as the bit which Alice sent. However, if it doesn't, this only will happen 25% of the time, because only half of the time will the two bits match, and out of that, only half of the time will the photon go through. So if this were all, in these cases, of course, she can simply let the photon go along to Bob, and then Bob, of course, if she blocked the photon completely, then Alice and Bob both would know that something is going on in between. So she can't afford to do that. Once she detects the photon, she has to let it pass through. So in the 25% of the cases, Eve can let the photon just go through to Bob. And just by looking at the photon, Bob will not know that there is a difference. But in the rest, that is in the 75% of the case, when she could not be sure what the state is, she will just have to guess what the state was. And she has no better information, so she might just as well guess randomly whether it's 0 and 1. Maybe just toss a coin. Prepare a copy of the photon in that state and send it to Bob, because Bob has to get the photon. Otherwise, if photons were missing in the middle of the path, they would know something has gone wrong. Now, in this manner, you can easily show this. I'm not going to the maths here, but this is simple probability. You can show that only 1/16 of the actual key can be learned by Eve. However, 1/16 of the key is actually quite a large fraction. Wars have been won by people who knew less of the key. They could manage to, because after all, codes have other information which can use to break them. So if 1/16 of a key is known, the key can almost certainly be compromised. But the important thing is Alice and Bob now share a key which is partly compromised, But what saves the day for them is Eve's action leaves a signature on the final key. Earlier, Alice and Bob would have to always agree about what
you
the
have
bit
5
was.
more minutes.
Okay, thanks.
5.
Thanks. I'm just ending. Alice and Bob would just have to have the same bit value for the photon to go through. But now that Eve has tampered with it in the middle, in 3/4 of the cases, she had to guess what the polarization state was and send that along randomly. There will be quite a few cases where where Bob will see a photon go through, but his bit will not agree with Alice's bit. So there will be errors. Now, what the two can do is simply randomly choose a section of the final correct results, final cases where they have matches, and share that publicly, share exactly what bits I have at those positions. Earlier, they were only sharing the locations where you had matches, but not what the bits were there. Here, what you can do is choose, let's say, 1,000 bits at random, 1,000 of the bits of the final key at random, and share them publicly. If Eve was not interfering, there would be no error. Or if everything worked perfectly, there would be no error. Or even if things did not work perfectly, you would know that there is a rough estimate of how many bits can go wrong. But because of Eve's action, if Eve really tried this, the amount of error would be much, much more. As a result, the two people would know that there has been an intrusion, and then they will simply say, and the important thing is Eve's measurement has changed the state of the photon, and this will lead to errors in the final key that they decide upon. And if they just randomly choose bits and share that publicly, they will get to know that there has been somebody who is trying to do this. Now, the whole theory, there are ways of other kinds of attacks which Eve can try, and there are ways of going preventing that and so on. The whole theory, of course, is much longer than what I've made it seem, but this is roughly the way things are. And this is roughly the reason why quantum key distribution works. If Eve were to try to intrude in between, even if she had the necessary technology, she will not be able to do it without leaving an imprint. Now, there's one thing that might strike a thoughtful listener here, which is, what if Eve just made a copy of the photon she got from Alice first, and then, now that she has 2 copies, she made an experiment, does an experiment on one of them, she sends the other copy along to Bob. That way, of course, no errors will be introduced. Of course, she will get the right answer only 1/16 of the time, as we said, but that's fine. That's still enough information for Eve. So couldn't Eve make clones of Alice's photons before measuring? The answer is no. This is where we have to go into the quantum mechanical properties of the system. Any non-disruptive operation in quantum mechanics has to be what is called unitary. You have to have a unitary operator acting on the state. And you can show that it's a very simple thing to prove, actually. It's a 2-line proof that non-orthogonal states cannot be reliably cloned by any unitary transformation. So the so-called no cloning theorem, which is a basic property of quantum mechanics, actually prevents you from cloning a system, cloning the photon which came in, and using that to break the code or break the key. Now, I'll just end with saying whether this is really theory or whether it has been done. Actually, it has been done. I'd already talked about Lee Smolin and Bennett's tabletop version. That was done only from one end of a table to another. But in 2009, a collaboration between universities of Cambridge and Toshiba managed this over 20 kilometers using optical fiber and at a rather large speed, 1 megabits per second. And frankly, that's nowhere close to the limit now. In 2017, Panji and Wei actually managed their distribution using a different protocol over 1,200 kilometers. In fact, there's a space mission, so-called Quest. The name QU, of course, is quantum. Created an international quantum key distribution channel between China and the Institute for Quantum Optics in Vienna. So we have had situations where people have managed to send a key from all the way from China to Vienna via satellite. Now, these are all laboratory experiments. Even the China to Vienna version is laboratory. After all, they were done with 2 labs, but it's not all that has been done. In fact, a bank transfer using QKD has been done in Vienna as long back as 2004. In 2007, the Austrian national elections, the results were actually transmitted to the capital using quantum encryption. And 4 companies, I think it's more, 4 was the case 2 years ago, I think it's 6 now, offer commercial QKD kits. People can buy QKD kits off the market and use that for quantum key distribution. And many more companies are actively doing R&D. And we, of course, don't know what the military is doing in any country. So QKD is definitely already here. Quantum computation is not yet at a stage where it can really challenge classical cryptography. That may come in the future, but its solution to that, the quantum key distribution system, is already present. And okay, I've come to the end of my talk. Thank you. And of course, the internet is a huge source where you can read more about this. And there are other places, other books and so on. Okay, I'm done. So if there are questions, I can.
Okay, thank you, Professor Dasgupta, for a very nice talk. And the floor is now open for questions. So if there are any question, you can either write in the chat box or raise your hand. And
Okay, I can see a few questions. One was a comment, Alan Turing cracked the enigma. Frankly, that's really not true, although that's what films would make you believe. The original enigma was cracked by Polish mathematicians. What Turing actually did was after the original enigma was cracked, Germans improved the machine by adding 2 more rotors, which made the original crack unviable. So Turing was part of the team, the major part of the team, which cracked the advanced enigma. Imitation Game is one film. Of course, I actually mentioned that films have been made on this. Another film has been made on this called Enigma itself. The Imitation Game is more about Turing's life. Of course, a major part of that is Enigma, but Enigma is another very important film. Okay.
Good morning, sir.
Yeah.
So I had a query regarding the RSA protocol. So
Yeah.
you said that for breaking the RSA, we have to factorize the n into q terms, right?
N into P
why?
and Q. Yeah.
Yeah. So why do we need to factorize it? We can just randomly generate all the values of t possible, and we can just keep it in a dictionary. Then whenever we have
but
to search,
do you realize that if you have a 400-bit number, 400-digit number, how many possible passes you would have to make for that? That would be factorization, actually. You could just keep on doing it until you get a factor. That is way more inefficient than the other algorithms which people have come up with.
we can just find the factors and we can just keep it in a dictionary. Then when we need it, we can just take it from the dictionary.
Wait a minute. You can find the factors provided you. How would you find the factors in the first place? The original person who generated it took to creating. Okay, checking whether a number is prime is actually pretty fast. So what you can do, in fact, that random number generation is very much part of the thing. 200-bit numbers are actually, these prime numbers are essentially generated by generating that random 200-bit numbers, 200-digit numbers, sorry, and then checking whether they're prime. That's actually quite efficient. Okay. But once you multiply them and give just the product, you will have to go through all possible 200-digit numbers before you can find the factorization. If you were to do this randomly. And the chances of that working is very, very small. You can easily figure that out. That's actually exponentially smaller than the more efficient methods.
Yeah.
It's simply not. Look, this is something which we find very difficult to understand because for us, we factorize numbers which are much smaller. And that seems to be something which gave us trouble as kids, but we can do it. At least with a calculator, we can definitely do it. Frankly, once you're dealing with numbers that large, and I told you, the current current record is 250 digits. Nobody, even with
Yes.
260 digits, have not been cracked yet. All when I say RSA 250, RSA 260, these are numbers which are already given out to people, created that way, and so that that's more as a challenge. Okay, now how are Bob and Alice communicating? Is there a string or telegram type communication on newspaper pages, and how is it? Communicating can be any way. When I say once the key is distributed, the key distribution occurs through a quantum channel, some kind of way in which photons can be transmitted from one place to another without changing the polarization state. That is, without changing the polarization state too much. But once the key is distributed, is decided, then you can communicate with each other openly. Doesn't matter. Because the ciphertext cannot be broken without knowing the key. And that is why Eve doesn't Eve can read the ciphertext as much as you want. That will not leave an imprint. Eve will leave an imprint if Eve tries to detect the polarization states of the photons being transmitted. And that's where quantum mechanics comes in. You cannot make a measurement without affecting the system, at least, unless you happen to make a very lucky measurement where the system is in an eigenstate of what you're trying to measure.
Okay, is there any other question?
So there are.
Okay, could you please read those out? And
okay. If Eve lets 25% the photons pass through and clones the rest 75%, clones the rest 75% is the problem. Cloning cannot be done. If cloning could be done, then there would be, then Eve could clone them at will and just send them along. There would be no errors whatsoever. And you would not be able to do it. That cloning cannot be done is a very important but very simple to prove result in quantum mechanics. It's basically standard linear algebra. Okay, I didn't get how did we conclude that there will be no transmission if they have the same bit. I didn't say that. I said there will be no transmission if they have a different bit. That is, if I were to go back a bit and just point out the basic protocol. Yeah. So if they're the same bit, there's a 50-50 chance of transmission. If they're different bit, then they're either being sent horizontally directed vertically or sent diagonally directed 90 degrees to that. No chance in that case. There is very much a chance of transmission when they have the same bit. In fact, the chance is 50-50. Okay, I think.
all right.
I think I've got most of them, but I don't know.
Okay, because I cannot see the chat box, the questions in the chat box. So maybe they were just directed to your chat box only. So if there is any other question,
there are direct messages, right? It's saying direct message.
Right. Okay, so if not, then let's thanks the speaker again for a wonderful talk. So that I will now hand over the mic to Dr. Ganguly. Please go ahead.
Yes, sir. Yes, thank you, Anand sir. Thanks, Dr. Anand Dasgupta, for this wonderful session. And it was really a privilege. I have listened to your talk in the YouTube channels and all, but it was really a privilege to listen to you live. And so thanks for giving this time to us. And thanks to Dr. Anjan Burman. Sir, you are a very busy person. Thanks for spending, almost 2 hours with us in this conference. So I would request Dr. Shomodipta Pal, to kindly to display the plaque of Dr. Anand Dasgupta. Yes,
okay,
sir,
thanks a lot. Okay, this looks great.
It's a
Even has my picture on it.
Yeah, it's a memento, sir. So